Welcome everyone. We are continuing our introduction to the really basic ideas of motion. We're going to look at vectors as well as speeding up and slowing down, what that means both in terms of objects, which is fairly straightforward, but also understanding that in terms of vectors. There's a misconception there, and our knowledge of vectors is going to help us hopefully sort through it. So let's go ahead and get started. First, vectors and scalars. Now, some measurements that we do in science, they include not just a value, not just like a number like 7, but they also include a direction. All right, one example is right here. Let's say that you're starting at your house and you're going to a shop, or you're giving directions to your friend. You're saying, okay, we're going to meet at this maybe bookshop. All right, and your friend asks, oh, well, how do I get there? It'd be silly if you said something like, walk 5 blocks, right? That's very unclear. Right? You would maybe say walk 5 blocks north, or leave your home, turn right, and walk 5 blocks. So displacement, comparing one position to another, displacement is a vector because you going up and to the right is very different. It's a very different displacement than going, say, down and to the left. So displacement one is one example. Another example is velocity. A car moving north at 50 miles per hour or 50 meters per second would end up at a very different location than a car moving, say, south at 50 meters per second. Since that velocity, that change in displacement over time, is affected by direction, we say that velocity is a vector. Okay? Now, other examples of vectors. I mentioned displacement, I mentioned velocity. Acceleration is an example of a vector. And as I said at the very beginning, at that very front slide, we'll look at an example comparing acceleration and velocity when it comes to speeding up and slowing down. Now, if something in physics is not a vector, it's going to be a scalar. And a scalar is simply a quantity that does not depend on, it does not include direction. An example is time. Okay, if you look up at the clock, you don't say, oh, it's 2 p.m. north. All right, direction doesn't affect the time on the clock. Okay, 2 p.m. north isn't any different than 2 p.m. south. You don't include direction. It's not needed, therefore time is a scalar. If you remember the last video on distance we were just adding up those individual like meter sticks or rulers. Distance is just the total length traveled, doesn't depend on direction. Similar to speed, if you think of just the speedometer in your car, all this dial is doing is pointing to a given speed. All right, speed is distance over time. Distance is a scalar, time is a scalar, speed is also a scalar. Doesn't depend on direction, okay? Now, when we're dealing with these vectors, these things that depend on direction, obviously it would be valid to talk about it when it comes to things like a conceptual question. Oh, an object was moving north at such and such velocity. But we also have to keep track of this direction when it comes to plugging into equations. And while you don't have to copy this down, the convention we're going to use is very similar to that you would see in a math class when it comes to like a number line or when it comes to a graph. If you think of a number line, classically, positive numbers are going to the right, negative numbers are going to the left. So to convey direction, especially when it's simple to start off with, right, left and right, all right, east and west, we're going to use the same kind of positive values and negative values that are used in mathematics. So to convey direction, we're going to use positive signs and negative signs. Like you can't include the word east in an equation. You can't plug into your calculator 5 north. But we can use positive and negative numbers. So we can use that to assign direction, and even better, your calculator and our mathematics are designed to use and incorporate pluses and minuses when it comes to finding value. So that's what we're going to do. Okay? We're going to use pluses and minuses to show direction. And by convention, things going to the right are the positive direction. Things going to the left are the negative direction. You're going to see me writing something like this down very often when we're doing these math problems that deal with vectors. Okay, so this is the key idea. When things are moving right, we'll say they're moving in the positive direction. When things are going left, that's going to be the negative direction. Same thing, up will be positive and down will be negative. At least that's the convention that we will mostly follow. So real quick example, super easy. I don't think you have to copy down both of these if you're taking notes. But let's say we have a car and it's going to the right, and it has a speed of 10 meters per second. Remember, speed is a scalar, so this is perfectly fine. Now, you might write down that the velocity of the car is 10 meters per second, you could write down right or east if it was like north, south, east, whatever. Okay? But if we were going to use our positive and negative convention, positive is normally to the right, you could write this as positive 10 meters per second. This is us representing the vector of velocity, 10 meters per second in the positive direction. Also, just like in math class, usually you don't put a plus sign for positive numbers. If you just wrote down this, that's conveying a positive 10 or 10 to the right. Well, let's look over here. Now the car is simply moving to the left. So the same speed, still 10 meters per second, it's moving to the left. What do you think we'd write down for the velocity? We're going to say negative 10 meters per second. And if we were using an equation when we were plugging in velocity, maybe we were using acceleration, right? That's v minus v naught over t. Depending on the problem, maybe this would go in the initial velocity, maybe the final, but you should include this negative sign. Okay, it has a velocity in the left direction. We symbolize left with the negative sign. That's all we mean about plus and minus and using it for vectors. Now let's talk about an example, a conceptual example, and it has to do with things speeding up and slowing down. We saw from the last video that when an object is accelerating, that means an object is speeding up or slowing down. All right. Now, both velocity and acceleration are vectors, and understanding this speeding up and slowing down is really based on understanding this velocity and acceleration vector component of these two terms. Okay, and here's what I mean. I have a car right here, and it's traveling, let's say, to the right. Okay, so here I've represented the velocity of the car with an arrow, with a vector. The length is actually like the amount. All right, if this was like 5 inches or 5 pixels or whatever, we'd say it's 5. And the arrow's direction is the, direction. So this is representing the vector of velocity. And let's say it has an acceleration to the right. Remember, acceleration is also a vector. So this is representing the amount and the direction of acceleration. And don't forget what acceleration means. Acceleration means the change in velocity. So what we have right here is a car moving with some velocity to the right, and it's experiencing a change in velocity also to the right. Well, what does that mean? If this is my velocity and I have a change in velocity of this amount, that means, remember, acceleration is change in velocity per second. In the next second, I'm going to have this. I'm going to have the original velocity, and here's the change, the new velocity. It's going to be the same length in the same direction. This would be after 1 second. The original after 1 second. After 2 seconds, I'd have this velocity, and here's the change in velocity. If we're assuming a constant acceleration, this is the next piece. This would be after 2 seconds. Here is the overall velocity of the car after 3 seconds and after 4 seconds. So in total, this acceleration after 4 seconds would lead the car to have this overall velocity. They're in the same direction, so the change in velocity is going to be going in that same direction. It's like you're adding up these arrows. So this is us showing the car's velocity increasing, going faster, and that's happening because the velocity was going to the right and the change in velocity was also going to the right. So if velocity and acceleration are in the same direction, the object was speeding up in this case. It was going faster and faster. This velocity, then this velocity, then this velocity, then this velocity. So that's an example, or that's showing us how vectors help display what it means for things to speed up. Well, let's look at an opposite, or at least a similar but key different example. All right, again, I have the car going to the right, so the velocity is going rightward, but now let's say it has an acceleration to the left. Ooh, now it has an opposite acceleration. Remember, acceleration means change in velocity. So if the velocity is going to the right, I have a change in velocity going left, which means now I'm actually going to have this velocity. I have almost like something canceling, because I'm going to go with this velocity, but I need to change the velocity this amount. I really think it's helpful to look at this in terms of numbers. Imagine this is like a velocity of 5, but now I have to go in the other way some amount, like a change of maybe 3, make up a number. And it's the opposite direction. So this is like 5, add with -3. 3 is canceling. So this is what I have left over. It's almost like that old version of like adding or subtracting numbers. This minus this gives us this. So this, with this change in velocity, gives us this amount. But another second later, again, if the accelerations are staying constant, I have to again cancel this amount of velocity. That leaves this little bit left over. So I put a star kind of like, this is the result showing the acceleration in the opposite direction. I'm still changing velocity, but now I'm changing it in the opposite direction. So it's canceling out. I go from this, then I have to cancel, and I have to cancel again. So the velocity is getting smaller. It's approaching zero, right? This is just a tiny little itty bitty velocity at the end. So if the velocity and acceleration are in opposite directions, objects slow down. Their speed is approaching zero. All right, let's look at some quick examples I have right here. So first example, some of these will be similar to what we just saw. Some of them will be different. I have a car. The velocity is going to the right, so it's going like this. The acceleration is to the right. Is this car speeding up or slowing down? It's speeding up. I'm just going to write down speeding. Okay, you don't have to copy this down if you're taking notes. Okay, this car is going faster and faster and faster. Let's look at part B. The car is again going to the right, but the acceleration is now going to the left. Velocity to the right, acceleration to the left. Speeding up or slowing down? Hopefully you say slowing down. These were our last two examples. Part C. Now the car is going to the left. Car is going to the left, but the acceleration is going to the right. Is this car speeding up or slowing down? It's slowing down because the velocity is left, but the acceleration is in the opposite. It's canceling, it's taking away, just like we saw in our last example. Lastly, part D. Is this car, if it's moving to the left and it has an acceleration to the left, is it speeding up or slowing down? The car is speeding up. Here's the key thing I want you to take away from these pictures. A lot of students think, oh, we're told that the object has a positive acceleration. That must mean that it's speeding up. That is absolutely not true. Likewise, a negative acceleration does not necessarily mean it's slowing down. Look right here. Here we have a car with an acceleration in the negative direction. Remember, positive is usually right and left is usually negative. Here we have a car with a negative acceleration, but it's speeding up. This idea of speeding up and slowing down, it's based on the combination of velocity and acceleration. So if you didn't copy down a lot of those pictures, and I know it's kind of difficult to draw in your notes some of those pictures when I was adding like one arrow at a time, you should absolutely copy down this chart right here. And if you don't want to write down all these words, at the very least, copy down these words here. This is the key. Okay, here I have velocity telling us whether velocity is in the positive direction or negative. Remember, plus or minus just means direction. Here I have acceleration in the positive or the negative. This is how we know whether an object is speeding up or slowing down. It's based on both velocity and acceleration. If there was a question and it simply asked, or it simply said, a car has a positive acceleration, is it speeding up or is it slowing down? You don't know. You can't answer that, because it's all about the combination, how the velocity and the acceleration vectors are in comparison to one another. If they're in the same direction, plus plus or minus minus, that means they're speeding up. If they're in opposite directions, plus and minus or minus and plus, that means they're slowing down. That's the key takeaway. So vectors can often lead you to come across some slightly difficult scenarios. This is, I think, the first one my students encounter. Okay, speeding up and slowing down, it's based on the comparison of the velocity of an object as well as the acceleration. I would absolutely copy this chart down. But that's my video. That's us talking about and introducing the idea of vectors and making sure we understand what it means for an object to speed up and slow down. Thanks for watching.